Okay, let's continue our discussion on Noether's theorem. Let me first remove this timeline. Okay. So, I had written down an expression for the conserved current, which is this here. Okay. And of course, even if I multiply J mu with some constant here, that will still be conserved. Okay. So, because you'll still get del mu J mu equal to 0. But we'll fix it to some level, okay, and you will see that I'm going to change the signs later, and we'll see the reason why. But for now, we'll just proceed like this. Okay. Okay. So let me give you one example of evaluating conserved current and corresponding conserved charge, and for that I will look at complex Klein-Gordon theory. Okay, so let me write example here. Yeah. So you have two fields now, phi and phi star. You can treat phi and phi star as independent fields. So d4x del mu phi star del mu phi minus m square phi star phi. Okay. So, and the symmetry which I am interested in is this one. Okay, so the symmetry is phi going to e to the I. Let me write, earlier I think I wrote alpha, but this time I will write epsilon to make the fact, sorry, just a second, phi, to make it explicit that I am looking at infinitesimal transformation. So this is 1 plus I epsilon phi plus higher order pieces. Okay, and similarly the phi star would be transforming as this. Sorry, here should be phi. Epsilon phi star, that is correct. Okay, and I think we have already discussed last time, that the k mu would be 0 in this case, right? Because the Lagrangian density here, that's not going to transform into something which will have a term which will be total derivative, because this is internal symmetry. It will not generate any del mu k mu term. Okay, so k mu is 0. So all I have to do is plug in this formula for J mu. There is a summation over I implied here over the repeated index I. So if you have several fields phi i's, okay, under the symmetry transformation, each of the field will transform in some way, and these are the corresponding changes, the coefficients of epsilon. Okay, so if you want, I can make this more explicit by putting a summation. Okay, it looks, how should I do that? Okay, let me try. I have never tried. So anyway, there was a minus sign here. So let it be like that. I will put a sigma here. Okay. So let's go here. So for us, phi i's are phi and phi star. Okay. So we have two phi's, and I should calculate J mu is equal to del L over, maybe I should write here, and I think I've been calling it psi. psi I. So psi, yeah. So before phi I, psi I of x, and then you have k mu, which is 0 in this case. So let's calculate what is psi of phi and psi of phi star. Okay, I am using this notation so that instead of writing 1 and 2, I imply psi corresponding to change in the phi and psi corresponding to change in the phi star. So that is I phi, from here you can read off, and this is minus I phi star. Okay, so here this will become, and when I take the derivative of Lagrangian density with respect to phi, okay, del L over del mu phi, del of del mu phi, that will give you a del mu phi star. So you get a minus del mu phi star, and then this one is I phi, so I times phi, and then you have minus, and this one will give you del mu phi, and the corresponding psi I is minus I phi star. So minus makes it plus I phi star. Okay, so which is I phi del mu phi star minus phi star del mu phi. Okay, and if you compare, you will see with some book, you will see that there is a sign difference, overall sign difference, and we'll see why there is difference. But there is nothing wrong in here, because clearly del mu j mu is 0 whether you have a sign here or not. Okay, so that's fine, and then we can construct j0, and j0 would be minus I phi, and this is del, I have to put mu equal to 0, so this becomes phi dot. And this becomes, this was phi star dot, this is phi dot. Okay, and your conserved current is this phi. What will that be? That will be gradient of phi star minus phi star gradient of phi. Okay, because the special components of del mu, that makes a gradient. Okay, this is fine. So you can write down now the conserved charge q, which is d cube x j0, and j0 is this, so I put a minus I phi del phi over del t minus phi del phi star over del t. Something wrong here. Let's check phi. Okay, so many things wrong. What did I do wrong here? Phi, this should have been starred. This is fine. So this looks okay. Okay, so that's the charge, and you know that dq over dt should be 0. Okay, but it will not be 0 for any field configuration. It will be 0 for field configurations which satisfy the equations of motion, right? So show that indeed you get dq over dt to be 0 upon using equations of motion. Okay, that you should do, and equations of motion are simple in this case. They are just del mu phi plus m square phi equal to 0, and del mu phi star plus m square phi star is equal to 0. Okay, so use these equations, put in the definition of q, and show that the total time derivative comes out to be 0. Okay, and that would provide you a exercise on understanding how and what Q is. Okay, so that will not be difficult actually to show that. Now this was internal symmetry and things were simple and nice. Now I want to look at translation symmetry in Klein-Gordon theory. Okay, and we'll talk more about translation in general, but let's first have some experience with translation and in a simple setup, and then we'll talk more about it. Translation. So here your Lagrangian density is half del mu phi. Probably this is the 1000th time I am writing the same del mu phi. Okay, so the symmetry we are talking about is phi tilde of x is equal to phi of x mu. I am just writing mu explicitly here, and I am looking at an infinitesimal transformation, and I can do a Taylor expansion here plus epsilon mu del mu of phi, or that's absolutely correct, but I will make it rho, it will be slightly comfortable, and plus order epsilon square terms. Okay, so that's the transformation we are looking at. So what is our psi of phi? What is our psi? We have four translations. Okay, epsilon 0, epsilon 1, epsilon 2, and epsilon 3. So I will put an index rho here, and let me put a bracket. So the psi corresponding to each of those transformations is just the coefficient of the parameter epsilon, so which is del rho of phi. Okay. Now let's take the Lagrangian density with phi tilde and del mu phi tilde. Okay. And what I want to do is I want to find out the K mu. Okay. So for that I do this calculation, and I'll just give you the answer. It's simple, so I don't want to do the full algebra here. So you get the density, of course, and plus epsilon rho del rho of L, okay, of the Lagrangian density. Now we don't want this form. What we want is epsilon rho. So imagine that we are taking only time translation, not others. So this would have been just epsilon 0, okay, and del L over del T. Okay, but what we want here is epsilon 0 times something which looks like del mu K mu, right? So I want to convert this into del mu K mu kind of a thing. Okay, so and that is not difficult. Let me tell you one thing. So if you have to raise or lower an index on some object, so if you have, let's say, a mu, and you want to raise this index to, let's say, rho, you use eta rho mu. Okay, that raises it. But sometimes you may want to just change the index on this one. So you don't want a mu, but let's say you want a rho. Then you don't use eta, because eta will raise it. Suppose you want to keep the new index again lower, but change it. So what you can do is you take a mu and write delta mu rho. Now this object is, this one is a of rho, okay, because mu is contracted. So this is how you can change the index by using a delta. Okay, this one of course becomes a of rho. So this is a of rho up, and this is a of rho down. So you start from the mu index down in both the cases, but here you end up with rho down, and there you end up with rho up. Okay, and that's what I'm going to use here. So I will write it as epsilon rho. Okay, and this del rho I write as del mu. Okay, this object is having an index down, but then I should have a rho rather than mu, so I have to have del mu of rho. So this del rho is these two things together, and of course you had your L. Okay, this is L plus, let me write it more neatly, del mu of del mu rho L. Okay, now this is in the form which we wanted. This is a form of del mu k mu. Okay, so k mu, but you have Vermont index rho because you have several, or rather 4 transformations. So each one has all the 4 terms are present here. Okay, so what is k mu then? Our k mu corresponding to each of the transformation which we are labeling by rho is del mu rho times the Lagrangian density. Okay, and if you want to look only at time translation, you can put only epsilon 0 to be non-zero and all the other epsilon 1, epsilon 2, epsilon 3 to be 0, and just look at the time translations. Okay, so let's calculate now the current J mu for each of these 4 transformations, if symmetry transformations or symmetries. So when you plug it in here, okay, we have other term also with the k mu. So you get the following. You get minus, so this is an exercise, you should show that you get minus del mu of phi del rho of phi plus del mu rho times Lagrangian density. Okay, and just a second, and this you can of course write as eta mu sigma del sigma phi del rho phi. Okay. So we have got 4 conserved currents. J mu of 0, J mu of 1, J mu of 2. This 2 means you are looking at translational symmetry along y-axis, and this 3 means you are looking translational symmetry along the z-axis. Okay, so these are 4, and they will give you corresponding q's. Q, let me call it 0. So that is d cube x J mu 0, and similarly these 3, let me put them together. Okay, some q which will be J mu. Okay, instead of putting a vector symbol here, it's better to put an I, and d cube x J mu of I. Okay, so these are the charges, 4 charges that we get, and these charges are called together they form a 4 vector, and they are called momentum. So they together form what is called P mu. So if you write Q0 and Qi, okay, these are 3, Q1, Q2, Q3, then they together form object which we call P mu, and these are defined to be the momentum of momentum carried by these fields. Okay, this is what becomes the momentum operator when you change the fields to quantum fields. But this is the conserved quantity is momentum, conserved charge is momentum for this theory. Okay, and in general you call it momentum whenever you are looking at space-time translations. Okay, and you will also see why we call it momentum, and you will see that when we are looking at the special Klein-Gordon theory, we are going to get the time component as really the energy. Okay, and that's why this name makes sense. So let's go ahead and sorry, I have made small mistake here. So this is not correct. Mu I have anyway put to 0, right? When you are calculating the charge, you put mu equal to 0. So here the mistake is here. It should be 0, and here it should be 0. Okay, and this is not the right index. The right index is rho. Okay, because it is this lower index which is relevant here. Okay, mu, there is no mu here. Okay, so this is the momentum in the Klein-Gordon theory, and let's define. So what is P? Not defined. Let me just write. So what is P of rho? It is d cube x j0 of rho, and this turns out to be, if you calculate, minus eta 0 sigma del sigma phi del rho phi plus del 0 rho times this. Let's check. Sigma is contracted, only rho is free, only rho is here, looks correct. Okay, and we can define this to be, there is no need to put a bracket around this, so let me call it P rho. Okay, and I can define a P with an upward index, okay, rho, and that will be P sigma rho sigma. Okay, and this will be, you can calculate this, it's easy, eta 0 rho times L minus eta rho sigma eta 0 tau delta tau phi and delta sigma phi. Okay, that will, you can work out from here. Let's check whether everything looks okay. Rho is the free index, sigma tau are contracted, rho is free. So this looks fine to me. And if you calculate now what is P0, okay, then you get integral d cube x. Okay, so I put rho equal to 0 here, then eta 0 0 is 1, so you get L minus rho is 0, let me write rho eta sigma, eta 0 sigma, eta 0 tau del tau phi and del sigma phi. Now this is easy, minus. So this term contributes only when sigma is 0, and this term contributes only when tau is equal to 0. Otherwise they are 0, which means this tau and that sigma are forced to be 0. Okay, so I get del phi over del t, del phi over del t. Okay. Okay, and you remember this Lagrangian density has half phi dot square as the first term from the del mu phi piece, and this minus makes it minus half del mu phi dot square. So this is minus half phi dot square, not del mu phi dot square, half phi dot square, and then this has already minus half gradient of phi square, and finally minus half m square phi square. Okay, and which is just minus of this entire thing. And you recall that the Hamiltonian is this piece. So we see that we have got P naught to be minus h, and that is what I was referring to here. Where was it? Here. Okay. So even if I change the entire sign, it is still a conserved current, and now you see that it makes sense to change the sign in my definition of conserved current, because then I will get P0 as the Hamiltonian. Okay, so I will change the sign now. So J mu I will write as del mu phi I psi I of x, and of course there is a summation over I and minus k mu. Okay, and this is so there was a plus k mu and I should have a minus k mu here. Okay, second. Okay, now when I do this, P naught will come out to be positive. So with this definition of J mu, the signs will come out right. Okay. P0 will be H. Okay, with the right sign. Okay, and of course you can also ask what is P, and I leave it as an exercise for you to check that this is pi of x times gradient of I. Okay, and this this gives you the momentum. Okay, now you recall long back we have used the expression of momentum when we were dealing with Klein-Gordon theory, the quantum theory of Klein-Gordon fields, and at that time I had just guessed what P would be based on Lorentz symmetry, and I had said that P, just looking at the Hamiltonian, so you recall if you look at the Hamiltonian, what we had written, it was dqp, and there was omega here, omega p, and AP dagger, AP, and of course some constant here. And then I have said that because this is it was kind of easy to guess that this you can replace by P to get the momentum operator. Okay, so this is the time you can check this. So exercise is this: you take this expression of P, which is a classical expression in the classical field theory, and promote phi and pi to quantum operators. Okay, so replace them by phi hat and pi hat. Okay, and express these in terms of A's and A daggers, and then show that this operator P which you get in the quantum theory is indeed this. Okay, so I leave it as an exercise to do. We'll continue our discussion more on Noether's theorem in the next video.